Let's solve some exercises from the exercise set 4.1. Here we have to prove some statements about natural numbers for all natural numbers using the principle of mathematical induction. Because most of the problems are similar, so they will be left to you. I will only solve one or two types. So let's consider this 10th one. Here we have to prove this identity. You look at the left hand side, it's a sum, a finite series where the terms go like this, 1 divided by 2 times 5. This is not decimal point, okay, this is multiplication symbol. 2 times 5 plus 1 divided by 5 times 8 plus 1 over 8 times 10 and so on. And the general term is this, which also is the last term here, 1 divided by 3n minus 1 times 3n plus 2. And to see that these numbers really are following this pattern, you can put some values and see. For example, if you put n equal to 1, here you are getting 3 minus 1, that means 2. And 3 times 1 plus 2 is 5, like that. Let's see another one. Say you put n equal to 2, then 3 times 2 minus 1 is 5, and 3 times 2 plus 2 is, that means 6 plus 2, that is 8. So that's how it goes. We have to prove that this series equals n divided by 6n plus 4. To apply induction, of course, first we have to go for the basis, which corresponds to n equal to 1. So when n is 1, the left hand side has just this one term, which is 1 divided by 2 times 5, that means 1 divided by 10. Whereas for that same n value, that is 1, the right hand side becomes 1 divided by 6 times 1 plus 4, so that is also 1 divided by 10. That means the identity is true when n is equal to 1. This is our basis. Next comes the induction hypothesis, where we suppose that the identity is true for some natural number k. That means this is true when n is equal to k. And then we write the left hand side with one extra term. That means we write all these terms and then the next one, which corresponds to k plus 1 in place of k. So we just write that here in place of 3k minus 1, we would have 3 times k plus 1 minus 1. And in place of 3k plus 2, we would have 3 times k plus 1 plus 2. And then we apply the induction hypothesis. This part equals k divided by 6k plus 4. And if you do the simplification here, it turns out to be 3k plus 2 times 3k plus 5. Then in the next line, we note that here the denominator 6k plus 4 is actually 2 times 3k plus 2. So here also you have a 3k plus 2. So there is an advantage. And now you take the LCM. 2 times 3k plus 2 times 3k plus 5. And the numerator then becomes what? These two things you already have here. So that means k times 3k plus 5 plus. Here you have these two things except 2. So that means 2 comes here. And then if you do the multiplication and manipulation, you get 3k squared plus 5k plus 2. Which equals, you can check this, 3k plus 2 times k plus 1. So now these two factors will get cancelled. And that then gives us this, k plus 1 divided by 2 times 3k plus 5 or 6k plus 10, which you can also write as 6 times k plus 1 plus 4. And you go back now and see the identity. This should be the right hand side if you write k plus 1 in place of n. That means we have proved the identity for k plus 1 based on the supposition that it's true for k. And you can write the final line. Hence, the identity is true for all natural numbers n by the principle of mathematical induction. So there the solution ends. Let's see number 22 next, where this time it's not an identity but it's a statement. Look at this integer 3 to the power 2n plus 2 minus 8n minus 9, where n is any positive integer, that means natural number. We have to prove that for any such n, this is divisible by 8. So in the solution, of course, first we see the case n equal to 1. We put n equal to 1 in this integer and calculate the value. You will see that it's 64, which is divisible by 8. So that means the statement is true when n is 1, and this is our basis. And then the induction hypothesis, suppose that the given statement is true for some natural number k. That means when you write k in place of n in that integer, that is divisible by 8, or in other words, it's a multiple of 8. So it equals 8 times m for some integer m. And then we consider the next integer of that form, which corresponds to n equal to k plus 1. That means 3 to the power 2 times k plus 1 plus 2 minus 8 times k plus 1 minus 9. So if you do the calculation here in the exponent, you get 2k plus 2 plus 2, that means 4. And here you get minus 8k minus 8 minus 9 becomes minus 70. And then what we do, you know what to do, you try to bring this thing here. From this, you already see that you have 9 times 3 to the power 2k plus 2. Because you can, well, actually you can do that here itself. You take 3 square outside. Outside means you just break it apart. Okay. So that way you get 9 here, and you are left with 3 to the power 2k plus 2. And what else did we do? Originally we have minus 8k, but here we have written minus 9 times 8k. So to compensate for that, we have also written plus 8 times 8k, so that we get minus 8k. And minus 81 plus 64 is minus 70. Alright. And then what we do, we take 9 common out from this part within parentheses. And that gives us this. Whereas outside the parentheses, we have 64k plus 64. So this part becomes 8m, so 9 times 8m plus 64k plus 64. The first term is of course divisible by 8, and so are these other two. So that means this is divisible by 8. So that means our statement is true for n equal to k plus 1 based on its supposed truth for k, n equal to k. So by the principle of mathematical induction, the statement is true for all natural numbers n. Let's see another one, number 24, where this time we have to prove this inequality. 2n plus 7 less than n plus 3 whole square. For the basis, we just put n equal to 1. Then this left hand side becomes 9, whereas the right hand side is 4 squared or 16. And obviously 9 is less than 16, so we have the basis. Next, the induction hypothesis. Suppose the inequality is true for some natural number k, that is 2k plus 7 is less than the square of k plus 3. And now we consider 2 times k plus 1 plus 7, which if you rearrange its terms, it becomes this 2k plus 7 plus 2. And then you use this induction hypothesis. 2k plus 7 is less than the square of k plus 3. So that plus 2 is less than this plus 2. Now you expand the square, k square plus 2 times k times 3, that means 6k plus 9. 9 plus 2 is 11. Now in place of 6k, if you write 8k, you are writing more because k is the positive integer. And in place of 11, you are also writing 16. So you are still writing more. So this is less than this. This, however, is the square of k plus 4. And k plus 4 is k plus 1 plus 3. So that way, this is less than the square of k plus 1 plus 3. That means our inequality is true for k plus 1 based on this induction hypothesis, which is the inequality for k. So by the principle of mathematical induction, this inequality is true for all positive integers n. And the video ends here. If you want me to solve some other exercise problems on mathematical induction, then you write in the comment section below. Next week we are going to start a new chapter.